Professor Yogesh Simmhan Anna is an associate professor at the Indian Institute of Science, Bangalore, specializing in scalable software platforms, algorithms, and applications for distributed systems. His work spans cloud and edge computing, temporal graph processing, and distributed storage, facilitating big data and IoT applications. Yogesh Anna, can you please share with us your view on AI for society? What are the challenges and opportunities?
I'm a faculty at the Indian Institute of Science, just half a kilometer from here. And as part of my day job, I do research. I work a lot with masters and PhD students. So I'm teacher to maybe 20, 30 students during my day. But I also play a role of a teacher in the evening with my 6-year-old son. Right? And many of the things that I tell both of them, right? These 20, 25-year-olds or my 6-year-old are pretty much the same. And today, I'm around students who are in the midpoint between that, right? So between your kindergarten and between your postgraduate, right? And here in your high school and late middle school and so on. But one thing I tell them is work hard. That goes without saying. Hard work will get you places, right? More so than brilliance, right? So work hard, you can be brilliant and lazy and get nowhere. But hard work will take you places. And be curious. You'll hear that again and again today. Right? Be curious, right? So don't take things for granted, right? Even if it's your teacher telling you something, right? Don't take it for granted, right? I tell my students that, right? I tell them, hey, I might tell you something, right? I might tell you based on what I might have learned a few years back or what I might have read 3 years back. I might have misread it or I might have forgotten, right? All this gray hair doesn't come without losing gray skills as well, right? So do go and check up, right? Don't take what I take for granted, double check it, triple check it, right? And I say the same thing to my son as well, right? I tell him, hey, I may tell you something, but do go and check it, right? Even though I'm your dad, right, and you're just 6-year-old, go and check if what I've told you is correct, right? And he does that, right? If I tell him something, he goes and asks his mom, did dad tell you properly? Is this correct, right? When his mom tells him something, he doesn't ask me, right? He trusts her, right? So she's much more trustworthy than I am. But you have to sort of go beyond what's taught in your school and by your teachers, right? Because there are new things out there. You can go to Wikipedia and you can learn a bunch of things, right? You can go to the internet and learn a bunch of things. Way more than what I as a teacher or your own teachers might be able to teach you in class in that limited amount of time, right? So go out and explore and learn new things, right? And I myself didn't go to an IIT or to an MIT before I landed up at IISc as a faculty. I went to a good school. I had some very inspiring teachers. I was interested in computer science at a young age. I probably saw my first computer in my life when I was about my 8th standard or 9th standard. Right? Till then, there weren't computers in India. Or they were probably in some fancy labs. But by the time I came to my 11th and 12th, I had a really inspiring computer science teacher, right? And she really sort of made me tap into my excitement of computer science. And I knew then that that's going to be my career, right? Through my life, I know I want to be working with computers. I want to be writing code. I want to be designing algorithms, right? And similarly, I went to just a local private college in Chennai for my undergraduate. But even there, for my final year project, I had a faculty who was inspiring me and my teammate to think big, right? Not look at your standard sort of projects that every other student was doing, but go beyond. It might be risky, it might be hard, you might fail, but it's okay, right? You have to sort of take on hard problems and do your best, right? As I say, unless you try to jump to the sky, right? If you try to jump to the sky, you might reach the ceiling, right? If you try to reach the ceiling, you might barely get off the ground, right? So dream big and work hard to achieve those dreams, right? And then, of course, I got the opportunity to do my higher studies abroad for my master's and PhD on a scholarship. I spent some time doing a postdoc at Microsoft, at faculty at USC, and so on before I came back to IISc. So I took a long circuitous path, right, to land up at IISc. But point being that it doesn't necessarily have to be you have to go to the top college or the top school in India or in your city or in the world to get to the top university in India, right, as a faculty, right? You can sort of work hard and sort of still make it to great places. All right, so with that, let's switch over to some of the technical stuff, and I'll come back to some of these sort of takeaways at the end. But let's talk a little bit about some technical problems around AI, right? So I'm not an AI expert, right? Though I'm here giving the starting talk on AI, right? Because one thing that researchers, and you'll find that from other faculty that you'll hear from today as well, as faculty, we claim to be experts on a very narrow area, right? As I say, as you start learning more and more and more, as you do your higher studies and so on, right? You end up knowing a lot about less, right? So I might have my expertise, which is more on distributed systems and so on, but we do apply it to AI. So I'm here as much as a learner of AI as a practitioner of AI, right? And there'll be many other talks that you'll hear about today that who are much better experts at AI, right? But at the end of the day, one thing that's useful to understand is that AI feeds on data, right? AI is here, the way we see it today, right? Because of all the data that's around us, right? And when I was doing my undergraduate, this is probably 25 years back, we had a course, we had an elective course called neural networks, right? And right now everyone talks about neural networks, right? But back then there was a niche problem, right? So 25 years back, neural networks was just offered, it was very theoretical in nature, it was very, very abstract, and not much came out of that, right? But fast forward 25 years, it's sort of the same concepts from 25 years back. It's been around for a long. The reason it's really kicked off is because of the availability of way more data today than we had 25 years back, right? So back then you had the techniques, you didn't have the input to the techniques to make it really work, right? So a lot of data, and AI at a very loose level of abstraction is about helping a software, an algorithm, a sort of piece of code, learn patterns, right? It look at data, look at a lot of data, and look for patterns, right? And it finds a pattern, it'll memorize it. It'll say, okay, I saw this pattern means something, I should remember that, right? If it doesn't see a pattern very often, it'll forget it, right? It's just like how you learn, right? If you keep practicing your arithmetic again and again and again, you'll be good, right? If you stop practicing something, you sort of lose your skill set. It's a bit like that. A lot of data helps it detect patterns and memorize it, right? And the data also tells it, right? So there'll be sort of data that says, hey, this is good, this is bad, right? And learns that as well. Not good and bad in the human sense, but good and bad in good quality data, good quality outputs and not. Okay, so let's see, right? Let's do a very simple, so one of the building blocks of AI or machine learning is a bit of statistics. A lot of it is based on math, right? So if you enjoy math, you'll probably enjoy AI, both learning it and doing research and so on. It's a very simple plot, right? So hopefully all of you have encountered a plot. If not, it's very easy to understand. So over here we're trying to see, as the temperature gets hotter, how much ice cream is sold. What do you expect? The warmer the day, the more you'd want to eat an ice cream. So more people eat ice cream. So you see a nice trend over here, right? So but if it's a cool day, right, you probably don't want to get ice cream. Right? If it's a warm day, you want to get ice cream. If it's a very hot day, you probably want to get a double scoop rather than a single scoop, right? So this is an example of a pattern, right? You can show this to a piece of, let's say, machine learning code, and look at this and say that, okay, I see, right? And then later on, if you come and say that, hey, today is, let's say, 30 degrees Celsius, it can give you a prediction saying that, hey, okay, today I think there'll be 50 cups of ice cream that's going to be sold, right? Or today, if you come and say it's 20 degrees Celsius, and say, okay, today I don't expect more than 2 or 3 cups to be sold, right? So that's the kind of pattern that it might tend to learn, right? Same thing, you could sort of have your height and weight, right? So if you sort of did that, you could sort of find potentially a loose trend between taller people they might be slightly heavier, right? And so on. But this might not be a strict trend, right? So this again, so this might be a more stronger trend than this one over here. And these are things essentially looking for patterns in data that the system learns. Right? And this is another example. This might be an example of various types of, let's say, how much someone might earn. This is how much someone might spend. Right? Some of you might be getting pocket money, right? So if you get pocket money, right, some of you might hold on to it and wait for the end of the year and buy something very nice, right? Some of you, the day you get your pocket money, the next hour you're off in the shop getting some coffee, right? So even over here, you could have people who might earn more and spend more, people who might earn more and spend less, people who might earn less and spend more, not good, right? And so this is essentially what you're looking at are clusters, right? So these are maybe 4 different clusters that are there in this particular data. So these are just examples of giving a lot of data to a piece of software, a piece of model, right? And having it learn that these patterns are there. Okay? All right, let's look at, and this is, as was mentioned, this is how even human beings, how all of us learn, starting from our being a baby, right? So we learn through stimuli, we learn through information that we get through our senses, right? When a child starts speaking, it may not necessarily understand grammar, it may not understand alphabets, it may not understand phonetics, right? But it's still able to make some sentences, right? It's able to make sentences because it's seen others, its parents, its friends, its relatives, make those same sounds, makes those same pattern of sounds. And it knows that, hey, if I say this word, right? If I say Anna, right? Or if I say Masal, right? It means that it's curds or rice, right? So it learns this and then it starts repeating it. It starts just sort of imitating you, right? And that's in a sense what machine learning is trying to do. And the more stimuli that you get, right? So the more you talk to a child or a baby, right? The faster it's going to learn, right? That's essentially giving it more data, right? And having it pick up the model more quickly, right? So that's broadly what makes machine learning tick, right? And now let's see if more data means you can build better AI, artificial intelligence model, or ML, machine learning models. Where does all this data come from? Right? And the data is all around. And sometimes this is called big data, right? Some of it is a bit of a marketing term, but it's always nice to say what's a lot of data? It's big data, it's more data, it's huge data, right? So, but where does all this data come from? So, some of you might be using social networks, maybe all the cool kids are using TikTok, the oldies like us might be using Facebook. But almost half the people on Earth, and probably most of the people who have internet connectivity, right, use some form of social media, right? And this has been growing over time, right? And when you're using social media, you're actually exchanging information, you're sharing information, you're putting videos, you're putting images, you're sending a message, you're liking something, and so on. So all this is a lot of information that each of us are generating as we are in social media interacting with others. Right? Same with Instagram or TikTok or so on. And this data has been growing phenomenally. Right? This, to me, was an interesting sort of thing to notice. Like during COVID or pre-COVID, right? So India had about 100 or so million users on Instagram. But maybe Instagram got a lot of people bored. COVID got a lot of people bored. You look a couple of years later, and that's almost doubled, right? So within about 3 years, the amount of information that we are generating on Instagram has doubled, right? And that's a big jump, right? Which means there's more data for, let's say, Meta or Facebook that owns Instagram as well to do their model training, right? So when someone comes and posts a picture and marks someone as saying, hey, this person is my friend Rahul, right? Or this is my friend Priya, right? So behind the scenes, it's actually learning. Hey, this picture, this photo in this face in this picture is Rahul and Priya. And the more such data that you get, right, the more it's going to remember that. And the next time when you upload a picture, it will automatically say, hey, looks like this face is Rahul, right? Is this correct or not? And we say yes. It says, okay, good. I've learned it properly, right? Or if you say no, you say, oh, okay, maybe I made a mistake. Let me learn better, right? So this is how, by giving data and also potentially giving some prompts and maybe some yes or no kind of thing to guide it, you sort of train such models or in the presence of large data. So the other thing is probably a lot of us watch movies online, right? So we might watch movies on Netflix or Prime. I might be seeing documentaries or other video content online, right? And a lot of that has AI happening in the background. So one, you're generating a lot of data, right? But things like captioning, right? So if you go look at a movie, or Netflix or Prime, you'll probably find a dozen language choices that you'll get, right? And earlier on, there used to be a lot of effort in doing sort of manual effort in types in terms of going from one language to another. But right now, a lot of it is automated, right? You might record the original thing in English or even Korean or Kannada, and if there are sort of machine learning or language models that automatically translate it from one language to another. Right? Maybe there's a human in the loop so that they do a sanity check, so you don't put some mistranslations as part of something that will go to millions of people. But a lot of the heavy work is already done for you. To the point where even the dubbing or even the sort of vocalization of that translated text can itself be done in a semi-automated manner. Right? So again, having a lot of data helps you build such large models. Some of the daily interactions that you might do, right? You might have seen your parents do phone pay or Google Pay or UPI transactions. Right? You go see a QR code in a shop, maybe for a 5 rupee sort of packet of biscuit, right? That you might go to a shop. It's just, earlier on, we used to sort of hunt around for change. Oh, I have 10 rupees, they have change for 5 rupees. All these things are gone nowadays, right? You go scan it, you scan a QR code, right? You pay for 5 rupees, and your transaction is done, right? But behind the scenes, what's going on, right? There's two data centers, one sitting in Delhi, other sitting in, one sitting in Hyderabad, other in Chennai, where all your UPI transactions go to, right? There behind the scenes is actually checking if you have money in your account, right? And if so, it debits that, right? They also check if there's a pattern of spending that is abnormal, right? Maybe someone stole your phone. Maybe someone is trying to make a fraudulent transaction, right? Maybe you rarely go to certain shops and suddenly there's a transaction from a certain shop, right? And that too for a large amount that it's not seen, right? So it's not just simple transactions that are taking place behind the scenes when you're doing a phone-based transaction for exchanging money. There's a lot of checks going on if there are some patterns of abnormal behavior, right, that it's not seen before, right? And all of this has to happen in real time. And here again, there's a lot of ML activity that's going on. There's a lot of pattern matching that goes on for it to detect. And all this has to happen very quickly, right? No one wants to wait for 5 minutes for something in the cloud to come and tell you, yes, your transaction was true or not. If you wait for more than 5 seconds, you're upset, right? You start looking for better internet connectivity and so on. You want things done in a jiffy, so all this has to happen automatically and fast, right? And likewise, things like the sort of other kinds of government data is there, like all the invoices and so on. IoT is another big source of it. IoT stands for Internet of Things, right? And what it is talking about is the fact that if I have a sort of smartphone over here, and probably some of you might be having that, many of the adults will be having that. That is probably more powerful than, it's probably 100 times more powerful than the computer I had 20 years back, right? And it's also things are getting affordable, right? I can sort of buy a fairly powerful computer for a few thousand rupees, right? Like a Raspberry Pi, it's about the size, it's about half the size of my palm, maybe slightly larger than a credit card size. And that actually has enough computing power to run an entire, it's almost equivalent of a workstation from a few years back, right? And what's ending up happening is that everything from your utilities, from your, when you have your power meter, your electricity board in your house, right? You might see all these panels with things. Earlier there used to be things spinning around, now it's more digital. You have digital LEDs that show you the current usage. A lot of these things are being upgraded to smart meters. So what's smart about them? So instead of, let's say at the end of the month, someone from BESCOM coming and making a noting of what's the power usage in the last 1 month, you're shifting to a point where as and when you're consuming power, right, it's immediately reported over the internet to the utility, right? So it's happening in almost real time. Every minute or every hour or several times a day, it can be reported, right? But why is this interesting, right? You're only going to pay a bill at the end of the month, right? Why should I have to report it much more quickly? So here, by having more data at a regular interval, they can start planning their power supply, because DESCOM itself has to get power from somewhere before they can give it to you, right? It's might be coming from some coal-fired plant, right? Somewhere. It might be coming from a solar plant, or it might be coming from some wind turbines, right? And they see that, hey, today there seems to be a slightly higher power usage than we are normally used to, right? They can actually start planning things better so that we don't have power outages like we saw earlier on in the morning, right? Because it helps you manage things. So the more advanced notice that you have, that there's going to be more traffic, as in the next session Abdul and Vijay will be talking about, or there's more power consumption that's required, you can plan things better. And here again, there is a lot of analytics that goes on, time series analytics, saying that, hey, here's a trend. Can I, if I've seen this pattern so far since the morning, from the morning till about 10 o'clock or so, can I predict what is going to be the power usage for the next 2 hours? Is it a normal day? Is it going to be higher than usual? Is it going to be lower than usual? And that helps me plan things. So IoT is just another way of saying that there's a lot of such information that comes from devices or instrument all around you, which you may not even be aware of. Right? Smartphone itself is a type of an IoT device, right? Because they continuously, if I have my GPS on, my location is being collected continuously, and it's sort of being pushed to the cloud somewhere in the back end where it's being collected. Right? Likewise with your power utilities. Likewise with even connected cars. Right? If a BMTC bus is going around, you actually have GPS fitted over there, so that in real time you can know the location of those buses. Right? So IoT can come in a variety of forms. Even the CCTV cameras that you might see in various road junctions in Bangalore, all of that is collecting data and pushing it in real time to a control center that's out there with the traffic police. So all of this talks about instruments and sensors and small computers that are all around us, within a city, within a house, within a building, right? That's continuously collecting data. And the data is being analyzed separately to take decisions, to help improve the efficiency, improve the reliability of various utilities and various services around us. And all of that was more from a citizen-centric perspective and so on, but even from a scientific perspective, right? There has been a dramatic growth in data, right? If you look at how science itself has evolved, right? So there are essentially these big shifts in way science is done. Initially, right, way back, science was very empirical or experimental in nature, right? You might have heard of the famous experiment where sort of balls were dropped from the Leaning Tower of Pisa, right, to see how long it takes to fall to the ground, right? They took a big metal ball, put it, measure the time. They took a smaller one, measure the time, right? And even more smaller one, measure the time. Right? And they found the time taken was the same. Right? You think that a big ball would fall much faster, while a small one drops slower. That didn't happen, right? And then they figured out that, okay, there is this notion of a acceleration, right? Your gravity has a certain acceleration, and that is constant, right, across the sizes of the thing. So that was an experimental observation. It wasn't some complex theoretical things like the E equal to mc square kind of Newton's law or Einstein's law of relativity and so on that came into play back then. Right? It was very observational in nature, right? So that's how the original science was. You observe things, you plot trends, and you draw conclusions based on that, right? About what science is. Then things started becoming theoretical. You started having some fundamental scientific principles, right? The law of conservation of mass, right? So how chemicals behave with each other and so on. So all these were theory that were developed subsequently from a more mathematical foundations to explain what we have been seeing experimentally, right? So that was the next big shift in the way science is done, right? That doesn't mean the empirical went away. Empirical still continues, but it's, you add on to that a theoretical way of explaining things. Because one of the nice things about theory, right? is that you can generalize it, right? While you can drop, let's say, metal balls from a tower, right? Another question is if I go and drop it from a tall building over here, right? Is it going to hold true, right? I don't know. I can come and try it, right? But can you go to every place on Earth and try this out? It's not possible, right? So for something that's experimental or empirical, to be generalized and say, yes, it holds everywhere on Earth, right? Or maybe everywhere in the universe, right? So you need to have more fundamental theory that comes out of it, right? But sometimes these experiments help inspire theory. You look at a lot of these things, even scientists have been doing, in a sense, this kind of pattern-based learning for a time. You see some patterns, and you say, oh, maybe it's because of this, and then you start finding out the theory that fits those patterns, and you come up with a theoretical explanation. And typically, this theory holds true for a large class of these problems. Then science evolved into something that's called computational science. Right? In fact, the department I'm part of is the Department of Computational and Data Sciences. Right? So computational sciences was sort of the third wave of science where you try to measure things. So one great example of computational science is weather prediction. Right? So you might be sort of getting news alerts saying that, hey, there's going to be big monsoon thunderclouds and thunder showers tomorrow, right? So be prepared for that. Or there's going to be a heat wave tomorrow. Be prepared for that, right? So how do they do that? Right? They do. It's not just a question of looking at the sky and sort of making a prediction, right? So they actually do a lot of measurements, right? They have satellites doing measurements. Right? They have ground stations making measurements of amount of sunlight, amount of cloud cover, the amount of rainfall, and so on, the temperature, right? They have instruments in the sea, right, that are collecting various statistics on the ocean. And they take all this information and they feed it into essentially a set of mathematical equations. So it's driven from theory, right? And then they say, okay, this is how things are right now. Let me try to fast forward, right? I'll essentially say I have this set of equations, right? And based on these initial conditions, right, the current behavior of things, let me try to fast forward things and see how it will be, right? And then this is actually given to large computers, sometimes even supercomputers like the ones we have at IISc. And they might take maybe hundreds of computers and hours together, and then they'll say, okay, this is how it's going to be in the next 1 hour, the next 2 hours, the next 3 hours, and so on, right? And based on that gives you a prediction, right? That you might see some nice animations of how the cloud is going to move in the next 24 hours or 48 hours, and that will tell you if there's going to be a rainfall or not in different parts of Bangalore or southern India and so on, right? So that's essentially computational science. It's a lot of math. It's what are called simulations. Simulations is essentially starting off with some initial set of observations, feeding it to some equations that describe how weather is going to behave, and will come out with a set of predictions on how weather is going to be in future. So it's very mathematical in nature. Right? Now the fourth wave, so the theoretical and sort of computational. So effectively computational builds upon empirical and theoretical. It looks at the empirical for observations, it looks at the theoretical for the equations, ties them together, and says, I will use that for predictions. Now data science goes directly to empirical, right? And says, I don't need much of the theory, right? But give me a lot of data, right? If you give me enough data, right, of all the weather patterns that we've seen in the last 100 years, right, then I can make a prediction just based on the patterns I've seen. Right? In fact, recently there was one of the first machine learning models, which is what data-driven science is, that was able to do a reasonable weather prediction. And weather prediction is one of the most complex problems out there, right? Because there are so many things that can affect the weather, right? But there was a machine learning based model that was able to give a reasonable prediction that's comparable to the computational model. This computational model typically needs a lot of data to give you a prediction, right? Data-driven model might need a lot of data to train the model, right? To see how these patterns are, to understand those patterns. But once you understood the patterns, if you're given a new set of observations of how the current conditions are, it can quickly give a prediction, right? Because it's already seen it before. It might just go and say, hey, this looks similar to that one. Here's how it's going to look, right? So data-driven science is about looking at a lot of scientific observations through things like instruments and even sort of crowdsourced observation where people might be reporting information, and then try to make a prediction based on building these machine learning models. Right? So, okay, some animation. One example of such large-scale data in science, right, is this Large Hadron Collider, right? For those who might have heard about sort of elements in your periodic table as part of your science course, right? So particle physics is about looking at what are the smallest pieces that make up an element, right? What is smaller than your protons and your neutrons and your electrons, right? You've heard of those, right? So what makes up the physical form that we see around us, right? How small can you go, right? And so far, a lot of that was based on theory, right? 50 years back, or even earlier than that, Einstein and a bunch of other physicists said, here's what they think theory tells us the particle should behave like, right? But there's no way to verify it, right? All the information, like everything was based on some sort of guesswork, right? So based on sort of indirect observation, right? But then, over time, they started using these instruments, right? And this Large Hadron Collider, which was about constructed 15 years back, right, in Europe, is like a big donut, right? So all of you might have had a donut, right? A nice, tasty dessert. But this is like a huge donut the size of Bangalore, right? It's a big ring, right? And it's actually a racetrack, right? So you would have, for those who like car racing, it's like a big racetrack, right? 60 kilometers in diameter. And what they do is they take these small atomic particles, right? And they make them race in this racetrack, right? They have a lot of energy that they pump in to make it go faster and faster, right? And they're a little bit, they want to have fun. So what do? They take these particles and make them go in opposite directions in the racetrack. Right? So think about it, if two of you are going at extremely high speed on the racetrack, but in opposite direction. When you meet, what's going to happen? Boom, big crash, right? And what do you think is going to happen? Let's say you're not driving it, you're driving it remotely, right? So what do you think is going to happen to your cars or your vehicles? Smithereens, right? So they'll blow up into small pieces, right? That's what they're trying to do with these elements. They say that, okay, the elements, I cannot look inside the element, it's too, I don't have the instruments to do that. But let me take these elements and have them go in opposite direction and crash into the ether. And the energy, the speed at which they crash, causes those elements to break up into smaller pieces. It's about atomic particles, right? And what you see over here is one such crash. They actually have these cameras that are recording this crash as it's happening. And then they replay it in slow motion, right? And they look at all these pieces that are flying out from the crash, right? And those pieces will exist only for a fraction of a second. Because after that, they'll actually merge with other pieces and they'll form other kinds of elements around them, right? But for those few microseconds for which these exist, they'll take these slow motion pictures. And then they'll study them, saying that, hey, I've never seen this before and it's behaving this way. But 50 years back, there was theory that said that if there's supposed to be this particle, maybe a boson, right? Maybe a muon, right? That's supposed to behave this way. And this particle that I've observed for an infinitesimal second behaves this way, right? So that gives me confidence that this theory actually exists in practice, right? And in fact, the Nobel Prize that went out a few years back was for the discovery of the boson, right? Which was always, in theory, it was known, but no one had ever seen it until that point in time, right? But the key thing over here, right, is that this is extremely data-driven. Every time they run this experiment, right, every time they record these trajectories, right, through this sensor recordings, they generate terabytes of data, right? And a terabyte is like having maybe one computer's worth of data, and they have many, many such terabytes for a single experiment. And then many of these experiments during a whole month, right? So they need to have a way to process this information, right? So they might run an experiment today, and it will take them the whole week to look at the data, analyze it, and then say, hey, I've actually discovered this particle. Right? So this again is very data-driven. This generates a lot of data. And nowadays they're going to a point where they have they figured out some of these patterns. They're able to more quickly decide, hey, there's this particle, there's that particle. Earlier it used to be very computationally driven. It used to take a lot of time to figure out these trajectories using various equations on large computers. But nowadays with machine learning, given that they've run many of these experiments, they have a lot of this data, they're able to figure out these patterns and detect them more quickly so that they can look for patterns they have not seen before, because that's where the interesting pieces are. If you've already seen a pattern many times, from a scientific discovery perspective, nothing new to see. But if you see a pattern you've never seen before, that might be a new discovery, right? And that's what they're trying to look for over here. All right, so let me quickly move on, right? Because we are running out of time. But broadly speaking, data comes in various forms. Data is challenging because there's a lot of data. Sometimes it might be very fast data that makes it problematic. Sometimes it may be very complex data that's problematic. And all these things make machine learning and data science a bit more difficult to do. So it's not as easy. It's not like you wave a magic wand and things happen. That's why there are a lot of smart people who are working on this problem, and a lot of excited minds who are working on this problem, so that you can handle all this complexity. Right? So data science itself, which is the fundamental science that brings AI, machine learning, and everything together, right? So I think of it as having three parts, right? So one is all the AI ML methods, right? So if you think of like neural networks, right, or large language models, right? So if you've heard of ChatGPT, right? All those things are examples of large language models. Those are all examples of methods, fundamental mathematical techniques that are used to come up with how to train models. And then you have the applications, because a lot of these models may need to be specialized for a particular application. Right? If you're doing physics, particle physics, you might need some specialization. If you're doing, let's say, healthcare, right? If you want to sort of figure out, can I look at a picture of your X-ray and detect something? Right? That might require information about radiology, or it might require information about the human physiology for you to understand that. Right? So the application where you're going to use this model is going to be important. Right? And lastly, you also need large computing systems to help you run these models or train these models. Right? So if you have a lot of data, it's a lot of work to go through the data, find those patterns, and train models. So that's going to take time. So you need to have good understanding of large-scale machines as well. Right? So ML falls at the intersection of data science falls at the intersection of all three of these. And I'm sure you'll be hearing a lot more about some of these pieces, some of these aspects later on today. Right? But let me sort of quickly tell you a little bit about larger systems. Right? How do you deal with such large machines? And for some of these, you need large-scale machines. Right? You might need GPUs or clusters and so on which such models are trained. In fact, some of these are here at IISc. Right? But the idea over here is, how can you solve problems collaboratively using many, many machines? Right? Because these are hard problems, these are tough data and computing problems. Can you solve them using a lot of machines? Right? And here, you need to sort of start thinking in a distributed manner. Right? So let's take a small example. Let's say you had to add up a lot of numbers. You had to add up 30,000 numbers. Right? How long do you think it will take, each of you? A few minutes, a few hours, maybe a day. If you make a mistake, you'll have to write again. Right? But let's say you could do it as a group. Right? Let's say I gave you all these numbers, printed out on sheets of papers. Right? Maybe one sheet has 100 numbers, and I give you 30 sheets. Now, if you had to do it as a group of 30 of you, how could you do it? Right? You'd start off, right? Maybe give each sheet to each one of you, right? 30 sheets, each one goes to each one of you, right? And now each one of you only has to add 100 numbers, right? That could be done maybe in 10 minutes, okay? So you add these 10 numbers, these 100 numbers, and each of the 30 of you comes up with one answer, okay? Now what do? You take those 30 answers and give it to one student, And that student adds up all those 30 answers together to get a single answer, right? And you get the right answer. So instead of one person adding up 30,000 numbers, you just split your problem into smaller pieces. Each one of you solves a small piece, gives an answer, and then you add up all the answers to get a single answer, right? That's, in a sense, how we use many computers together to solve many of these machine learning problems, okay? So, being familiar with systems and computing systems and programming that works on such large machines is one part of machine learning as well. So I'm going to leave you with maybe one last video to show how some of this ML happens. Obviously, I had way more slides than I could cover. In the interest of sort of keeping time, I'll just show you one video that might be sort of useful from a real world perspective. This is a project that's going on in our group right now. And this is about using machine learning and drones, right, for helping people who might be visually challenged, right? So you might have seen people who are visually challenged or blind, who might be having a white cane that they help them navigate. Sometimes you might see them with a guiding dog that might help them around. So one thing that we're sort of playing around with is to see, can you use a drone to follow such visually challenged people and tell them about their environment, or if there's some danger ahead, or to help them guide along the streets and so on, right? That's one of the projects we're working on, and we are using machine learning as a key part of that, right? And what we do is that there's a camera in the drone. The drone is behind the person, right? And the camera sort of captures the video frames of the person and their surroundings. And this video itself is given to a machine learning model to help it detect both the person as well as their environment, right? And if it sees something, let's say a cycle that's ahead of them, right? Or if it sees some obstruction, it'll tell them, hey, there's a problem over here, go around it, right? Or if it sees that they've fallen down, right? It might immediately detect that and send an alert to their friends or family, right? But all of this, and it also is the same video feed is also used to control the drone so that it automatically follows them. There's no one controlling the drone. The drone sees the person, but its seeing is essentially doing some kind of a machine learning based inferencing, right? And then it sort of tries to follow them. Right? So I have a quick video which I'll show for that. You have to click the play button, I think. And this is led by Simmhan, who's a PhD student in my group. And what you'll see is a drone outside our department that's going to be following an intern. Okay. That didn't quite work out as I expected. All right, so maybe it didn't get copied over properly from my laptop. But what you would have seen is, and you can sort of talk to me later on and give me a break if you are interested, is the drone actually following the student around and being able to respond to that. Right? So it's examples like these that will help get machine learning to have social impact. I mean, each one of you is benefiting from machine learning in one form or the other as we speak. But there are other more socially relevant examples that are going to come in as well. Right? So with that, I'm just going to go to the last slide and leave you with a few takeaways. Right? So computational thinking is important. So think methodically, think algorithmically, be very analytical in your thinking. These things are extremely important if you want to do science, if you want to do math, and if you want to do data science as well. Math is foundational, so if you enjoy math, great, you're already halfway there. And likewise, programming, if you like programming, if you like liking code, that's again helpful. Curiosity and hard work, immeasurable, right? So one of my colleagues sort of has a very nice sort of saying that I'm going to borrow, right? There are two kinds of students, he tells, right? So some are like sheep, some are like goats, right? And typically sheep tend to follow, right? So if you have a couple of sheep going ahead, they'll actually follow that, right? So it's a bit of a herd mentality, right? Goats are a little bit obstinate, right? Goats are very hard to, you rarely see goats go together. If they go together, it's very hard to keep them on track, right? So Giant always says, you should have to be like a goat. Don't just follow the herd, right? Don't just do things because your friend is doing it or because the industry is saying do this. Do it because you have made up your mind that that's the right thing. And making up your mind might mean getting in information. It might be from your peers, it might be from your teachers, it might be from your parents, it might be from your news media, the internet. Make up your own mind, right? And chart your own course through life, okay? And you will do wonders, okay? Thanks a lot.
Thank you very much. Thank you very much, Professor Yogesh Simmhan. What you did was, I think, make things simple for everyone. And what struck me was, it's artificial intelligence with real emotion. If it's going to help someone who's, visually challenged. Thank you so much. Let's have a big round of applause for Yogesh Anna.